Every time we want to leave Earth, we strap humans to a controlled explosion. We point it up. We hope. A rocket is not elegant engineering. It's barely controlled chaos. It burns more fuel in the first minute than a commercial airline burns in a year. It fights gravity every single second, and when it's done, we throw most of it away. The rocket falls back into the ocean. We build a new one. We do it again. Getting 1 kilogram of anything into orbit costs somewhere between $2,000 and $10,000 depending on the rocket. 1 kilogram. The weight of a water bottle. $10,000. We have been doing this since 1957, and we have never found a better way. But here's the thing. There is a better way. There has always been a better way. You build an elevator. You anchor a cable to the equator, you run it straight up into space, you attach a counterweight on the other end, and then you press up. That's it. No explosion, no fuel, no falling back into the ocean. Just a box climbing a cable, all the way to orbit. The math works. The physics is proven. The blueprints exist. Engineers have known this was theoretically possible since 1895, so why more than a century later are we still strapping people to rockets and hoping for the best? Before we get to why it's hard, we need to kill one idea that sounds obvious and is actually catastrophic. You might be thinking, just connect a cable from Earth to the moon. The moon is already up there. Use it as the counterweight. Simple. Here is why that would end in disaster within hours. The Earth rotates once every 24 hours. The moon orbits once every 27 days. These two things are not synchronized. They are not even close to synchronized. If you connected a rigid cable between the surface of the Earth and the moon, the Earth would spin underneath it. The cable would wrap around the equator like a rubber band being twisted by a child, except the rubber band is made of steel, and it's wrapped around a planet. The tension would build in minutes. The snap would be catastrophic. You'd have a steel cable whipping around the equator at thousands of kilometers per hour, tearing through everything in its path. Cities, ships, anything in low Earth orbit. It would be one of the worst engineering disasters in human history, and it would happen before the cable was even fully taut. So no, not the moon. The moon is not the answer. The answer is something far stranger. Here is how a real space elevator actually works. You forget the moon entirely. Instead, you think about a very specific altitude. 35,700 kilometers above the equator. At this exact distance, something interesting happens. An object in orbit at this altitude takes exactly 24 hours to complete one full orbit, the same 24 hours it takes the Earth to rotate once, which means from the ground that object appears to hover. It doesn't rise, it doesn't set, it just sits there, perfectly still, directly above the same point on the equator forever. We call this geostationary orbit. Every satellite dish you've ever seen pointed at the sky is aimed at something sitting at this altitude. This is where your space elevator lives. You anchor one end of a cable to a point on the equator. You run the cable straight up 35,700 kilometers to a station sitting at geostationary orbit. And then you keep going. You extend the cable further, out past geostationary orbit, and at the end you attach a counterweight. A captured asteroid works perfectly, something massive enough that its outward centrifugal pull balances the downward gravitational pull of the entire cable below. The cable is now under tension in both directions simultaneously, gravity pulling the lower half down toward Earth, centrifugal force pulling the upper half outward into space. These forces balance. The cable stays taut, the cable stays straight, and a mechanical climber, something like an elevator car, grips the cable and rides it upward using nothing but electricity. No fuel, no combustion, just a motor and a cable. Now, let's talk about the scale, because this is where your brain starts to have trouble. 35,700 kilometers straight up. To give you something to hold on to, the diameter of the Earth is about 12,700 kilometers. That means the cable is nearly 3 full Earths tall. Stack the planet on top of itself 3 times and you're still not quite there. The International Space Station, which we consider to be in space, orbits at about 400 kilometers up. The space elevator cable would extend nearly 90 times higher than that. It is not a tall building. It is not a tall anything. It is a structure unlike anything humans have ever attempted, in a category entirely its own. And we haven't even talked about the hard part yet. The hard part is this. The cable has to hold itself up. This sounds obvious, but the implications are staggering. A cable hanging from space to the ground doesn't just need to support the weight of the elevator cars climbing it. It needs to support the weight of the cable itself. Every meter of cable has to bear the weight of every meter of cable below it, and the cable is 35,000 kilometers long. Let's think about steel first, because steel is what we build everything with. Steel cables hold up suspension bridges. Steel cables lift elevators and skyscrapers. Steel is strong. But if you tried to build a space elevator cable out of steel, something brutal happens. You can calculate exactly how wide the cable would need to be at the top to support itself all the way down. The answer is that the cable at its thickest point would need to be wider than it is possible to manufacture, store, or launch into orbit. Some calculations suggest the base of a steel cable long enough to reach geostationary orbit would need to be so incomprehensibly massive that the structure would collapse under its own weight long before you finished building it. Steel fails. Titanium fails. Every conventional material we have ever manufactured fails the same test. The cable, no matter what you make it from, snaps under its own weight before it gets close to long enough. Then, in 1991, a physicist named Sumio Iijima was studying carbon under an electron microscope and stumbled onto something that changed this conversation entirely. Carbon nanotubes. A carbon nanotube is a sheet of carbon atoms rolled into a cylinder about 1 nanometer wide. 1 nanometer is 1/1000th of a meter. These tubes are, pound for pound, the strongest material ever measured. A cable made from carbon nanotubes would have a tensile strength roughly 100 times greater than steel at 1/6 the weight. When researchers ran the numbers, a carbon nanotube cable could theoretically hold itself up across the distance required. The math worked. For the first time, there was a material that could actually build a space elevator. Except for one problem. We cannot manufacture carbon nanotubes longer than a few centimeters. We need 35,000 kilometers. The longest carbon nanotube ever grown in a laboratory, under perfect controlled conditions, with every resource available to modern science, measures in centimeters. The gap between what exists and what is required is not a gap. It is a chasm. It is the difference between a match and the sun. Researchers have been working on this problem for 30 years. We are nowhere close. And let's say we solved it tomorrow. Let's say someone figures out how to grow carbon nanotube cables at industrial scale. The engineering nightmare is only half the problem. Then come the politics. The space elevator has to be anchored on the equator. The equator runs through countries like Ecuador, Colombia, Brazil, Kenya, Indonesia. Whoever owns the anchor point effectively controls access to space for the entire planet. Every kilogram going to orbit, every satellite, every mission to the moon or Mars or anywhere beyond passes through that cable. The geopolitical implications make the Suez Canal look like a neighborhood dispute. Then there's the debris problem. Low Earth orbit is already cluttered with thousands of pieces of defunct satellites and broken rocket stages traveling at 28,000 kilometers per hour. Any one of them hitting a cable under tension that stretches 35,000 kilometers could cause a catastrophic snap. And a snapping cable at that scale doesn't just fall, it wraps. It becomes a gravity whip. It tears through the atmosphere at speeds that make a hurricane look calm. The damage would be planetary in scale. So here is where we actually are. We know the physics works. We have known since 1895. We know what material we need. We have known since 1991. We know where to build it and roughly what it would cost. Everything is understood except the one thing that makes it possible. We are standing at the bottom of a gravity well, staring up at a cable we can design perfectly and cannot manufacture at all. The blueprint is complete. The factory doesn't exist. Every rocket that launches today is a reminder of that gap. Every controlled explosion fighting gravity, every $10,000 per kilogram, every piece falling back into the ocean is the universe telling us we are not there yet. But the math is waiting. The cable is designed. And somewhere in a laboratory right now, someone is growing carbon under an electron microscope, trying to make it just a little bit longer.